AP Chemistry, Unit 2.7, VSEPR and Hybridization. So VSEPR is valence shell electron pair repulsion theory. That's what VSEPR stands for. And it is used to predict the geometries of molecules, so what shape actual molecules take. And the shape that the molecules take is whatever minimizes the repulsion between the electrons. So you can get that directly from what VSEPR is titled, valence shell electron pair repulsion. Okay, so we are trying to minimize the repulsion between those electrons. When we are dealing with our VSEPR, we are able to determine polarity. And there are a couple of rules for if a molecule is going to be polar or not. The first rule that you need to know is that molecules with only nonpolar bonds are always nonpolar. I don't care what the shape of that molecule is. If everybody is sharing equally, the shape does not matter. It is going to be nonpolar. Also, if molecules where the central atom is symmetrically surrounded by identical atoms, it is also going to be nonpolar. Even if the bonds between the central atom and the surrounding atoms are polar in and of themselves, if we are symmetrical, then I am going to be nonpolar. And then the last rule is going to be asymmetrical shapes with polar bonds are going to be polar. So symmetry is going to be very important, and then the polarity of the individual bonds. But if I am asymmetrical and I have polar bonds, then I am going to be polar. And then as a reminder, my lone pairs can cause asymmetry. The lone pairs offer more of a repulsive force than individual bonds, so they can go ahead and push down on the angle and cause bond angles to become smaller than they would be if everything around that central atom was a bond rather than having lone pairs present. Hybridization is the concept of atomic orbitals going ahead and hybridizing and mixing to form a brand new shape in order to allow for bonding to occur. In general, the sum of the superscripts of the hybrid orbitals are going to equal the number of electron domains that are around the central atom. And then we have sigma bonds, which are always going to be our first bonds that are formed between two atoms. That means any single bond is going to be a sigma bond. And then you have pi bonds, and pi bonds are going to be the second and third type of bond between two atoms. And those are caused by overlapping p orbitals. And so pi bonds are going to come from when you have double and triple bonds. That second and third bond would be a pi bond. Again, for single bonds, that is just one sigma bond. For a double bond, you are going to have a sigma bond form first, and then you will have a pi bond. And for triple bonds, you will have one sigma that forms first, and then two pi bonds to finish it out. These are all of the types of hybridized orbitals that you can have. So you can have SP, SP2, and SP3. These are going to be the most common. Technically, you can also have like SP and D also being involved, but we're mostly going to focus on SP, SP2, and SP3. Again, we are dealing with a number of domains, and those add up to be the superscripts of the hybridized orbital. So if I only have one domain, I don't have a hybridization. This is just the s orbital overlap. And just one single bond, nothing else coming off of either atom. We only have one electron domain, and so therefore not really hybridized. We would just be dealing with s. If I have two domains where either I have a lone pair or I have multiple bonds coming off of the central atom, then I have two things coming off of the central atom, and so sp, we have an invisible superscript of 1 for both s and p, so 1 plus 1 is 2, and that is the number of domains. Same thing for sp2. We have 3 domains coming off. We can have 3 bonds. We can have a lone pair and 2 bonds, or a bond and 2 lone pairs. Any way that you go ahead and add it up, we have 3 things coming off of that central atom, and we have sp2 hybridization. and we have, again, an invisible 1 on the S. So 1 plus 2, that gives me 3. That is the number of domains. 3 domains is going to be sp2 hybridized. And then for sp3, we have 4 domains coming off here, either 4 bonds, 3 bonds and a lone pair, 2 bonds and 2 lone pairs, or 1 bond and 3 lone pairs. Any way you slice it, we have 4 things coming off of that atom of interest, and so we have our hybridization as sp3, 1 as our superscript for S, 3 as our superscript for P, so 1 plus 3 gives me 4, and that is my number of domains that are coming off. Important thing to note for hybridization and for identifying hybridization for any particular atom is you could be asked the hybridization of any atom within a molecule. It is not exclusively central atoms only. So you could be asked the hybridization of any atom within a molecule, whether it is the thing that most of the other atoms are branching off of or not. So make sure that you are practicing identifying hybridization for all of the atoms within a molecule rather than only the central atom where everything is branching off of.